Welcome back to the video series. In this video, we're going to have a look at the Fourier transformation and how that relates to what we call the momentum representation of a wave function. As always, if you like the video, please share it, subscribe, write a comment. That helps drive up the visibility of the content. And with that, let's have a look at the exercise from last video. So the exercise from the last video was to numerically calculate the Fourier transformation of psi. So let's go ahead and do that. I've installed Comfit. I'm using version 196 for this video. So let's just import Comfit as CF and then import NumPy as NP. And Fourier transformation is available in NumPy through the command that's called np.fft. So let me create a quantum mechanical system. cf.quantummechanics in one dimension between -10 and 10. And let's also configure the initial condition as we've done before. Let's just use position at 0, width equal to 1, and initial velocity equal to 1. Then we know that qm.psi is going to be the complex field with arrays. And to get the Fourier transformation of that, which we will denote psi-f, we just do np.fft.fft qm.psi, essentially. So this will give us a variable psi-f, which is just a complex field, but it's the Fourier transformation of psi. So that was the exercise. So the topic of this video is what we call the momentum transformation and how that relates to the Fourier transformation. So let's just go into the Fourier transformation first so we can have a look at that. So the Fourier transformation is a different way of representing a function where you represent the function in terms of its wave numbers instead of its position coordinate. So the expressions look like this in the infinite domain. So psi-f, it's a function of the wave number, is this expression here, 1 over 2 pi, the integral from -infinity of psi-x e to the minus ikx dx. And then you can go back and if you have the Fourier space function, you can do the inverse Fourier transformation to get back to your original function. This factor of 1 over 2 pi here, it doesn't always appear in the transformation here. Sometimes it appears here, and sometimes it's a 1 over the square root of 2 pi in both cases. It just has to be somewhere, and I'm using this here, which is a convention. But you'll see the effects of that convention later. So both psi and psi-f are functions that represent the wave function fully. So if I give you psi, you know all there is to know about the wave function, and if I give you the Fourier transformation of the wave function, you also know everything that is to know about the wave function. So both are valid representations of the wave function. So let's look at the momentum representation and why the Fourier transformation of psi is called the momentum representation. So if you look at the inverse Fourier transformation, where we have the Fourier transform of psi, and then we get back the original wave function, what we see here is that it's an integral over these Fourier components multiplied with e to the ikx. And if you remember back to video 3, we looked at plane waves and saw that this is actually a plane wave. So remember, a plane wave is a function that it's this expression here, e to the ikx, and it's a constant function. Amplitude is always 1, but the phase changes from 0 to 2 pi, and then it goes through all the colors, and it has a wavelength of 2 pi over k. And so the momentum of this plane wave function, according to de Broglie, is h bar k, go back to that video if you didn't follow this. But if we now look at the inverse Fourier transformation, we can see that if we discretize this integral as the sum over k values, so we replace the integral with the Riemann sum, we see that actually we can look at this original function as a sort of sum over these wave number amplitudes multiplied by the corresponding plane wave. In other words, how much of psi of x consists of the wave number of e to the ikx. So how much of the wave function consists of this plane wave with momentum h bar k. And so if we look at this, expression here, so here is the wave function, and we remember the Born rule, which was that if the wave function looks like this, then the integral from x1 to x2 of the absolute value squared of the wave function is the probability of measuring the particle with a position between x1 and x2. In the same way, when we get to the momentum representation, we can say that the integral between k1 and k2 of this function here, and then there is a factor of 2 pi, which just comes from the convention we had with that, then this is the probability of measuring the particle with momentum between h bar k1 and h bar k2. So let's just calculate and visualize psi f for a couple of different wave functions. So we already have one. So we're going to create a subplot structure so we can look at both of them simultaneously. So let's do fig x is equal to qm dot plot subplots, and we're going to have one row, I think, and then 2 columns. Yes. So this creates a plotly figure object and an axis object, which we're going to be used to plot the wave functions. And then we're going to do qm dot plot complex field qm dot psi. This is here, and then we're going to specify, yes, exactly, that it's the x equal axis 0. And then we are going to give it a title. So this is the position representation. And then we're going to plot the complex field of psi f2, and it's already suggesting something for me here. Now, yes, let's just have a look at this and just show what it gives. So here we have the position representation. So this is what we're used to. This is kind of the wave function that we're used to. We see the probability the particle is located somewhere here. It has a velocity because of the phase gradient in the position. Now, the momentum representation looks kind of strange, and it also has this x over a0 on the x-axis. And that has to do with the fact that the Fourier transformation as given by this here is not exactly the same version that you will find in an infinite case. But the way to visualize it in a way that's sort of true to the physical nature of it is to pass the argument Fourier equal true to the plot complex field function. That will cause it to plot the Fourier field in this way here. So here you can see that so here we have in the Fourier representation we have kx on the x-axis, which goes from minus 15 to 15, and it's in units of a0 to the negative first power. Whereas here we have the x-axis, and it's in units of a0. Now, what's to be noticed about this is that since we gave it an initial velocity, so it has this phase gradient, it means that the momentum representation is not centered at 0, it's actually centered at 1. and due to the limited resolution of this, it sort of looks like the peak is at 0.93. It should actually be at exactly 1, this peak, but it just shows you kind of the velocity of the particle. If I, for instance, increase this velocity here, so let's say I increase the velocity of the particle by giving it a velocity of 2, then you can see that the phase gradient is now twice as high, so that it has a shorter wavelength. And then you can see that represented in the fact that this wave function has now moved further to the right. And we can continue this. So if I give it a velocity of 8, then the phase gradient will be very large. And now the wave function or the momentum representation has moved all the way over here. Let's do we can do a negative velocity 2, negative 4, in which case the phase gradient is now pointing to the left. So it goes from 0 to pi over 3, 2 pi over 3 in this direction. And now you can see that the Fourier transform of that wave function has moved to the left. And of course, if we give it 0 velocity, then it's just centered at 0. So there's that. The second thing we can have a look at is that if I let's give it a velocity again. So let's give it a velocity of, let's say, 2. So the other thing we can show here is that there is a relationship between how wide this wave function is and how wide this function is. So if I make the width of the Gaussian smaller, let's say if I say the width is 0.5, then you can see that the width of the wave function increases. In other words, the width of this wave function is an expression of how certain the position is, right? So if it's very narrow, it means that we're very sure of the position of the particle, but we know from the uncertainty principle that in that case, the uncertainty in momentum should become larger, and that's exactly what we see. When this gets narrower, this gets wider. I can make it even less wide, so a width of 0.1. Then you can see that we have a very sharp wave function in space, but a very sort of spread out wave function in terms of in the momentum representation. And it also goes the other way around. So if I give it a large width in real space, if I give it a large width in real space, then we can see that the momentum representation gets very narrow. And the way to, or one way to understand this phenomenon of this trade-off between the precision in position space and momentum space is that if you remember, this momentum representation sort of tells you how much of the wave function is of this given wavelength, right? And the wider this function becomes, the more the sort of position representation consists only of this one plane wave. I mean, if I exaggerate a bit and put the width to 0, you can see that the wave function essentially just looks like this plane wave function, and that's why it only picks out this one point here. The other way to think about it is that if you have a very small width, then it's very hard to say exactly which sort of plane wave this is consisting of. I mean, if it's for instance, if it's just 0.1, then you can see that it's almost like just red here. So it's very hard to tell exactly which plane wave this function consists of. So that's that. So given this definition of the momentum representation, we can get back to expectation values. And in particular, we can look at how to calculate expectation values in momentum space. So exactly the same way that you are allowed to calculate expectation values of the momentum operator in real space by using the momentum operator, we can use the momentum operator in momentum space, in the momentum representation, to calculate the expectation value also there. And so in the momentum representation, the p hat operator is just h bar k, essentially. And so in order to get the expectation value, we do the same thing. We do the complex conjugate of the wave function multiplied with the operator acting on the wave function. And then we need to integrate over the full region, which is 2 pi, and also have this 2 pi due to the convention here, dk. And so yes, so one of the ways to show that you actually get, I think I meant to say this for yeah. So what you can do here is that, exactly what I was trying to say here is that if you now take this and you insert the expression for psi f in terms of psi, you can insert that into here, and you can show that it results in the same in this expression, and there, of course, we recognize this as the operator in position space. Now, the point that I was mentioning earlier was that there numerically, when you do something like the FFT of psi, it's not exactly the same thing as the Fourier representation in the infinite case. And the reason for that is that this Fourier transformation that you do on a computer is a highly efficient operation called fast Fourier transform, discrete fast Fourier transform, which is not the same as this idealized infinite thing. And they are related, and they are related by this expression here, namely that this infinite case psi f object is 1 over n, where n is the number of points, multiplied by the digital spacing of the k vectors, and then e to the minus I k dot x0, where x0 is the starting point of your simulation, and then multiplied by this sort of digital Fourier transformation. This is not very important for the physics of it, but it's just I wanted you to know this, and there are more details on this on comfitlib.com if you want to have a look at how that relates. Anyway, so essentially in the plotting functions, when I'm passing Fourier.true, essentially I'm compensating for that in order to visualize the function as if it was the infinite version of it. So now you know where that comes from. So now let's go to the programming, and we are going to verify this probability interpretation of psi. And then we're going to verify that we can calculate the expectation value of the momentum, both in the momentum representation and also in the real space representation. So let's go back to the Fourier representation. So this is the thing we need to calculate, except we need to do this properly. So let's go back to here, and let's start with a function that is let's start with a function that is not as crazy. So let's just use this. So a width of 1 and initial velocity of 2. So it has a phase gradient, and this is the momentum representation. Now, as I told you, in order to use these expressions here, these integrals, we need to get the actual infinite series wave function out of it. So I'm going to do that by looking at, first I'm going to get dk. So in Comfit, this k vector number, this k space here, the k space onto which we are plotting the momentum representation, are represented by this qm.k object. And qm.k consists of as many arrays as there are dimensions. So in the case of one dimension, it's just one object in here, and k of 0 is this object with the wave numbers. The point of this is that if I take out the first element and then I subtract the 0th element of this, then I get the spacing in the k space. That is dk. So this right here is dk. And secondly, I need the number of points, which is given by xres. So I need to do 1 divided by dk, or qm.xres, that's the resolution in the x direction, multiplied by this discrete Fourier transformation. This is this object here, and then I need to multiply it by this in order to get the thing which I can integrate. So let's do that. So I need to multiply with np.exp of minus 1j times what is it? K multiplied with x0. So k multiplied with qm.xmin. I think that's what that's called. So now we have, k is not defined, qm.k. So now we have turned this discrete Fourier transformation function into the thing that for which the probability interpretation applies, and now we can essentially just integrate the whole thing. So the first thing we're going to do is just like integrate the whole thing as we did with the because remember, if this interpretation here holds, that the integral of psi f between k1 and k2 is supposed to be the probability of measuring the particle with momentum between those values, then obviously if I integrate over all of k space, then I should get 1. So in particular, it means that if it's properly normalized, then we should have that the integral from minus infinity to infinity of psi f conjugates psi f 2 pi dk is equal to 1. So let's just check that first. And obviously we can do this quite easily. We just write, just integrate the whole thing. np.sum. This is the Riemann sum integration. Apps of psi f multiplied by psi f. And then we need to multiply by 2 pi dk. I think this should be correct. Let's see what we get. Pi is not defined. We get it from NP, I think. Yes. And so you see we get 0.9999999, which is almost 1, and then the imaginary part is 10 to the negative 14, which means that it's properly normalized. So there's that. So that's the probability interpretation. Yes, another thing is that if we look at the function, we see that it has a momentum which is probably around 2, right? So the peak is at around 2. We can do like a conditioned or like a limited integral the same way we did for x space by saying that the interval we're interested in is qm.k of 0 larger than, let's say, 1. So this is going to pick out all the k values where the wave number is bigger than 1, and we multiply that with the k values which are smaller than 3. So this is going to pick out the interval between 1 and 3. And then we can do the same sum as we did before, only now we restrict ourselves only to the interval we're interested in, and then we get 0.941, which means that it's 94%, we have a 94% chance of calculating the particle between momentum 1 and 3, which we kind of see here. And if we instead look at the probability between 5 and 10, for instance, then we get that the probability is 1 to the 10 to the negative 10th. So there's like no probability of measuring the particle here. So let's calculate the expectation value of the momentum in both ways. So in Fourier space, this is quite easy. We almost have it already. We just need to take this thing we have here, and then we need to multiply by h bar times, let's see, what's the expectation value? H bar k. That's the representation in momentum space. So k of 0, like this. And of course, we have set h bar to 1 in our all simulations, so we just remove it away, and we're left with this value here, except k is not defined. It needs to be in qm. And we get that the expectation value for the momentum is 2, which makes sense because we have made this to have that initial velocity. So px momentum space. We can also calculate px in position space, and for that we need the p hat operator, which we defined previously. So I'm just going to borrow that from here. So p expectation value position space is equal to, and then we need to do the same thing. We need to integrate the absolute value of, first the complex conjugate. Oh yeah, by the way, I realized that this kind of looks a bit strange because I took the absolute value of psi f multiplied by psi f. I should really do the complex conjugates of psi. So I think it was, the reason that it worked is that in this case, the Fourier space representation is actually, it's actually a real function. So that's why it didn't bother with that. But in reality, it should be conjugate here, here, and here. So let's do, and also for like visibility, let's also move this one here. It shouldn't make any difference. So let's calculate the psi f, and then it's suggesting something for me. Is it correct? So we're going to do, no, actually it's not psi f, the conjugate of psi, qm dot psi. And then p hat applied to qm dot psi, that's correct. This we don't want here, but we want to have qm dot dx here. So this is the expectation value in position space. And now let's just print the two statements. Expectation value in momentum space. Right. And now it has respected this. We're going to take the real part just because that's what we're interested in. So let's have a look. And we see that the expectation value in momentum space is 2, which is exactly right. And the expectation value in position space is 1.93. So it's almost 2. It's not exactly. And that, of course, as so very often happens, has to do with the limited numerical resolution. If I increase the resolution, so I think by default it's 101 time steps. So if I do xres equal to 1001 time steps, for instance, then we see that these two values approach each other. So that's p in both ways. So here we've sort of seen the thing, right? So the Fourier transformation of a wave function is its momentum representation, and we can use both to calculate different expectation values and switch back and forth between them. So for the next video, the thing I want you to do is a analytical exercise, and that is to try to write the Schrödinger equation on a dimensionless form, which means setting h bar and all those things to 0, or like taking out the variables, and then gets dt psi alone on the left hand side. So that's the exercise for the next video, and good luck with that, and then I will see you in the next video.